Okay. All right, I think we'll start. Otherwise, we'll be late for lunch. Okay. So what now we are going to do? We looked at, remember, state vector measurable actor critique, right? With 3 neural networks. And we saw one was identifier, and you need 2 more neural networks. Then we went to the case where the state vector is not measurable. This is a case, very typical, practical case, right? And then we did that part of that. So now we are ready. So now what I'm going to do is, I'm going to use the same affine system. I'm going to look at how do I design an optimal controller. The network is lossless, but we have quantization. And we're going to use the dynamic quantizing. You got it? We're going to use the dynamic quantizing. Okay? And then we also would deal with what we call actuator saturation. Now, actuator saturation is a big problem. Because a lot of times, you design a controller, the controller would give you a very high control input. Whereas you don't, in the actuator doesn't have that bandwidth to convert that command into either a voltage or a current signal, you see? So that's the problem. So actuator saturation is a very common problem, many practical situations. Now what is the alternative when your actuator saturates? You have to physically change the motor if it's a motor. And sometimes when you make the motor bigger, it becomes a load on the robot or the case. That's the reason why many times we are very careful about actuator saturation, okay? Then we also have quantization, okay? So online finite horizon, this is what we are trying to talk about it. So here is the system. Remember we saw the system, x of k plus 1 is equal to f of x of k plus g times x of k. And then here you see that this is a quantized input. Got it? And yk is equal to c times x of k. We assume that the system is controllable and observable, the same stuff, okay? And uk is through a quantizer, all right? So here is the performance index. The only difference is you see that this is non-quadratic. This WUI, this is non-quadratic. So that means that if it's quadratic so far, we made it as uk r times uk. That's quadratic so far we have been doing. But now, I'm going to define it like another function like this. W of uk equal to 2 times integral 0 to uk, phi inverse of v transpose r times dv. And what this is doing is, it's basically limiting the actuator output within a certain limit. Okay? So there is a saturation limit. It basically limits the control input between a lower bound and the upper bound. So this is non-quadratic, okay? This was taken from this paper, Levitsky, Optimal Control of Nonlinear Continuous Time Systems, Design of Bounded Controllers via Non-Quadratic Functionals, okay? So this is basically designed, this term. So this term is used here instead of quadratic, and then you have the Q, and then here is the terminal constraint. This is basically the value function. So this equation basically uses non-quadratic cos functional to accommodate the actuator saturation. And so non-quadratic, this is an example of a non-quadratic function we use as part of the value function. It's for finite horizon, okay? And we also want to handle, along with actuator saturation, we also want to handle the issue of quantization. All right? So now, so this is the Lipschitz condition. You see that the Lipschitz condition keeps popping up everywhere. So now you form that equation into what we call the Bellman equation, which is a recursive equation, Q plus W plus V star. So you see that the Bellman equation essentially should be V star. So the time at k to n minus 1 will be time k to k plus 1 plus k plus 1 to n minus 1. Okay? So that's the Bellman equation. So now, because of the actuator saturation, for W you have that function, and then you have that, and then optimal control input is given by minus phi. That phi basically truncates the actuator output. Okay, so that's a function that truncates between minus something to plus something. You see that? And that's based on the actuator. Okay, so we don't have that phi before. This phi is now here, and then you have the optimal control input. So that phi was not there. This phi is coming from this phi, and that's basically for the actuator saturation, to accommodate the actuator saturation. Okay? So it's shown in this paper with non-quadratic cos functional 3, the control input 5, that's 5 here, is indeed an optimal control that minimizes the value function 4, which is given by that. Okay? So now we'll start looking at the quantizer, dynamic quantizer. So remember the dynamic quantizer equation, QK is QD, the mapping to Q of K. So that's in a dynamic quantizer. You basically taking a mu k here and mu k is a zoom parameter. Remember the zoom parameter, we did that. And the purpose of the zoom parameter is what? What is the purpose of the zoom parameter? To bring the values from outside the range to bring it inside the range. Don't forget that. Okay? So that's the zoom parameter there. So we have the zoom parameter, and there's an error, and that error is given by this term, is bounded, and the scaling pattern mu of k is defined as expected value of absolute value of uk over lambda. So lambda is between 0 and 1. So the signals to be quantized can be scaled back into the quantization range with a decaying rate of lambda k. So this is why you have these equations, 4.64, 4.65 and 4.66. So those three equations, what that does for the dynamic quantizer, they push the values outside the range into the inside the range, so there won't be any saturation. And the good thing with the dynamic quantizer is you need fewer bits. We saw that before, and as you increase the bits, the error goes to 0. Okay, so this is the dynamic quantizer equations. So now we are going to go into the controller. So here you see that we have the V hat, which is basically the critique, and we have the Bellman error. You can see the Bellman error equation. You also have the terminal constraint equation, and you have the total error, En of k. Remember, the total error is the Bellman error plus the terminal constraint error. So we are using that to tune the weights of the critique network here. So this is the update law for the critique, which is given by equation 5. And this is the value function, right? And then here is the Bellman error. Now, since this is the output feedback, so this is the output feedback. Now look at that. The output feedback, essentially you are replacing the measured state with the estimated state. Don't forget that. Remember I showed you that, right? Because we don't have a measured state. Alright? But we use an observer. The observer design is from a few slides before I presented the observer design. And so the dynamic quantizer design is also there. This is the observer design. So only thing is I'm replacing the state with exact. Okay? So I'm computing the Bellman error. Bellman error uses the estimated state. And it also uses the extra term, which is non-quadratic functional, to accommodate the actuator saturation. Alright? So here is the terminal constraint error, and so the update law now uses the estimated state, the non-quadratic functional, and so this is the update law. Then you also do similarly, you also do the control input approximation, control input error, u1 hat minus u2 hat. Now look at that, it uses the exact, which is the observer state, okay? And then you are also updating the action network, which uses the input error or the, remember EUK here. So you're using everything, observer state, also the input error. Input error also uses the observer state. And it also quadratic, non-quadratic, the phi. You see the phi there? The phi was not there before. The phi is coming here because of the actuator saturation, to accommodate the actuator. So it truncates the value of the command input that goes into the actuator. You see that phi, and you select that phi. So now you have two flowcharts. One flowchart is with the actuator saturation and input quantization. On the right hand side, there is no quantization. Okay, and there is no actuator saturation. But both uses the observer. Both use the observer and the identifier. So you see that first you initialize the observer states, the weights, you have the system dynamics, then you are using the quantization, in this case the dynamic quantizer, you have the update of the observer, then you have the identifier, then you have the value function update, then you have the critique neural network. Okay? So you have the value function, the critique update, and then you have the control input. And action neural network update using this UU, and here is the Bellman error, terminal constraint error, here is the Bellman error update. And then you check the time. If the time is reached n, if time is not reached the final n, then k becomes k plus 1. Here k equal to k plus 1. And then you go back. Okay, so you see that there is an input quantizer here. You also can use a state quantizer. Okay? Here, there is no quantizer. So you basically observer, identifier, value function critique update, and control input. So basically there is no quantizer. So that's the difference between there is no without quantizer and with quantizer. Got it? So you show the mathematical results in these theorems. So let's take an example. So now we pick the same tooling robot. So the tooling robot that I defined here, we remember that tooling robot example. This is the tooling robot. Okay? So we are using the same tooling robot example. Alright. So now what I'm doing is I'm also looking at the actuator saturation. So I'm defining this value here. Okay? And the bounds on the saturation bounds are phi. Bounds is 1.5. So I chose the magnitude of that saturation. You can pick that based on the actuator. Alright? So sampling interval is equal to 5 milliseconds. Alpha 1 is 0.7, beta 1 is 0.01. The critique learning rate is 0.1. The actor learning rate is 0.03. The lambda value for the dynamic quantizer decay rate is 0.9. The Q weighting matrix is 0.1 identity. The R weighting matrix is 0.005. The terminal constraint value xi is equal to 3. Remember, we have to choose the observer A matrix, which is 0.9. You see that 0.9 is within inside the loop, inside the unit disk. So therefore, the eigenvalues are 0.9 is stable. Discrete same. You understand that, right? So the observer gain now, L equal to is selected like this. So that A minus LC, the eigenvalues are on within the unit disk. Any questions here, guys? Any questions there? Yeah.
Why we choose the observer gain? We will follow the simple pole placement.
Yeah, pole placement A minus. Yeah. A minus LC. You know C, we know A minus LC should be within the unit disk. Yeah, what is your question?
Sir, in the Bellman error which we defined, so there like we have the non-quadratic function forms.
Right. So here is quadratic, just to show you, this is not quadratic, here is not quadratic.
Right, so that's just the computation part, but the actual application of that phi function is in the
Control input. Actually, there is a derivation, and that's what the paper I cited. He showed that in the derivation, it only shows up in the optimal control input. So it basically scales the optimal control input. And the purpose of the scaling is so that it will be within that actuator limits. You see what I'm saying? The very similar idea we are using in the dynamic quantizer by using the mu. is right. You have to pick based on the how you want it. So one example is the tangent hyperbolic. So you can pick a tangent hyperbolic. The good thing with that is it's very smooth and continuous. And or sigmoid, like used in neural networks, you know. So you can pick any of those functions. Basically, it has a negative and positive side, and in between that is nice smooth function. You do want to pick a smooth function because it has to be Lipschitz, and it should be a one-to-one. So if you take the inverse, inverse should exist. So we call that term a smooth function whose inverse exists. What is the type of? There's a word that's being used in nonlinear control. How many of you took the nonlinear control class? And nobody is now raising. I see some people nodding. So you took nonlinear control? Did you take it here? Okay. So how about you? But did you take a course? The nonlinear control. So how many, other than her, she's bored at least. She's honest. How many of you have taken nonlinear control? All of you have taken. So what is that name? They use a name. So the function is one-to-one mapping, and then when you go back also it has to be one-to-one. Yeah, I know. Yeah, what is that called? Nonlinear control. We use that. That's very important. Because when we do the transformation, then we go backwards. So it has to be continuous, both sides, and it should be one-to-one mapping. So what is that called? Imagine, I'm even older than you guys, right? I remember. That's the learning part. You should be remembering that. See, in an interview, what do? If somebody asks you this question, let's say in a job interview. Yeah. So what is that called? Have you heard of diffeomorphism? Doesn't ring a bell. Go back and check it. It's called diffeomorphism. Diffeomorphism. Check that. Okay? So what it means is the function is smooth, so you can map it from one set to the other, and the function has to be. And where does it come? In feedback linearization. Did you guys study feedback linearization? Is that ring a bell? No? Okay, what did you guys study in the nonlinear control then?
Neither. They are knowing, but this time they are not able to reconnect. Because
So I'm positive, guys, right? We teach feedback linearization.
yes, that is there.
Yeah. So in feedback linearization, we map from one coordinates to the other. So that mapping has to be continuous, one-to-one. And then after you get the results in the other set of variables, you map it backwards. And unless it's a diffeomorphism, you really can't do a one-to-one mapping. So I want you to go back to your nonlinear control notes or whatever, check it. And I'm going to ask that question tomorrow, right? Check it. I think it's important. These are all very, so all these concepts are also there. I don't teach them here, but those are needed. We normally don't deal with them, Okay, so any other questions? Okay, about the Bellman error? Any other questions there? Is that clear? Yeah. So remember that Bellman error uses that actuator saturation stuff as well as the quantized state. Remember that, right? Because there's no normal state. So everything is a quantized state. So you have to use that in the Bellman equation, okay? And then if you don't have the quantizer, then you don't have to. In this case, there is a quantizer, okay? All right. So, but it also uses output feedback. That's why you have those hats coming in. You see there's a hat there, there's a hat there, okay? So that's the observer state. So we do that. And in the update class, you have the critique update, which is very similar form, but you have the Bellman error with the quantized state, and then you also have the action error. But you see that you're right, there is the phi there. That phi comes in because of this term phi is because of the actuator saturation. Okay? And then you have that, all right? So let's go back to the example here. So we are using a tangent hyperbolic function here. You see that? The tangent hyperbolic is what normally we use. So there is a tangent hyperbolic. U is the limit, and this is the actual value. This is the bar U. Okay? So now we have all these values. So now you can plot, you run the simulation, you can plot the error history, and you can see they nicely converge. So there are 4 states, converges. The quantization error also converges to 0. So now this is without a static quantizer, there will be error. This is what we are trying to show. There is error here. See that? This is, I think, 4 bits or something. And you can see the Bellman error converges, the tenor constraint error converges, the critique weights converge, the actor weights converge. So this is with the output feedback, and the system dynamics unknown. Okay? I think that's all I have here. Any questions? I think the only thing I didn't plot here is the observer errors. So maybe it's there, but I didn't plot and copy that plot here. So that I did the plot of the observer errors. But you know, in the other case, I have all got in the other examples that I showed you. They have the observer errors, right? Yeah, I see. There's an observer error here which goes to 0. And also in the other example, there is also the I think in the other example, I also plotted an observer error. So here I didn't plot it. Okay? Okay, any questions, guys? That's the quantization part. Any questions?
Sorry, this is in slide number 50. We have taken 3 neural networks only.
We use neural network. That is
Three
Yeah.
replicating and directing.
Yeah. And the actuator is all of the neural network and guide, and the V is the tangent hyperbolic. So it uses same neural network. That's why I presented without quantization before, and then I added the quantization. That is correct. Uses the neural network. Okay, any other questions, guys? Any other questions? Alright, sir.
Sir, here you have considered the actual saturation.
That is true.
The saturation means you are taking it out of the saturation by that dynamic tuning factor.
No. There are 2 kind of scaling factors. One is the actuator saturation. We use the non-quadratic function. See this in here, we are using that this is a non-quadratic cross function. So this non-quadratic essentially, which is taken out from this paper, revision. So this paper essentially you can select, right? Normally we select a quadratic function. This is what normally we select. Unconstrained. So with the constraint on the actuator, you basically change that this W function the function becomes non-quadratic.
What is the nature of this phi function?
It's a diffeomorphism. It's basically a diffuse. Tangent hyperbolic is what I think. That's what I was saying. You see that it is a diffeomorphism because phi inverse should be bounded 1-to-1 and phi has to be bounded 1-to-1, you know. So it has to go back and forth, yeah.
Tangent boundary.
Yeah, tangent hyperbolic, yeah. So that's what I did here. If you look at the example. So you see that tangent hyperbolic? And U is the limit.
So this will help not to cross the
That is correct.
saturation
Saturation limit, that is correct. So here we are doing two things. One is we incorporated that stuff to accommodate the saturation issue. In addition, we also dealt with the dynamic quantizer for the control input. You see?
The ADC part you are doing by June.
That is correct. That's right. So when I was covering this optimal control earlier, I said you could have some constraints. And one of the constraints could be on the control input. Because sometimes you still can produce a control input outside that range of the actuator. So the goal was, how do we bring it within the, just like the quantizer one. Any other questions? Any other questions? So we also added the observer part. You see that? So we had some on state feedback. I'm also showed you some on output feedback. You see that? Because output feedback is very common in practice. We won't have sensors for every state, right? So this is the reason why I said that I was covering both state as well as the output feedback. And there is MATLAB code. You can play with it. Okay, any other questions?
Sir, I have some implementation regarding the question. So
Okay.
basically, in aerospace control system, for actual saturation, we mostly use NDI controllers or ED controllers.
What controllers?
Non-linear dynamic inversion.
Okay, yeah, inversion. But you know, inversion controllers have some issues.
Yes.
Yeah.
So if we are implementing that and we are implementing this driven control system, so if I am comparing whether, because I have never used this, but I have used the non-linear dynamic inversion.
Right.
So which will the give optimal performance and prevent
Okay, I would not use inversion. I know in aerospace that's very common. And you know, inversion is always a problem, right? Remember, many reasons. One is, if the inversion is not exactly, then you don't get an identity.
Yes.
Usually the idea was, you have the nonlinearity and you are trying to invert that. And so that phi inverse phi is identity, right? That's basically the idea, and becomes linear. But there are, I know in aerospace I've seen that, but there are issues. Suppose there is some perturbation, then these two exactly doesn't match, you know? So that's the problem but even what I presented here was the actuator saturation still holds good. You can still do that, even with that type of setup, the inversion-based controllers.
But still, inversion-based controller, derivative.
I would not suggest, I would not recommend, because there are problems with inversion. Because what if the dynamics have some singularities? Right? Yeah. I know that in aerospace they limit, there's a guy, I forgot his name, he was in Georgia Tech, he does quite a bit on inversion-based controllers. And I had a lot of discussions with him, like he was doing helicopter control, and he was using inversion-based. There is a problem. If there's a little deviation, then, if they don't match, you get an extra term in there, because of it doesn't perfectly match. But here we don't have the problem. Because here the only idea of the inversion is mainly what you're doing is you want to make sure that you're pushing the actuator controller output values within that limit. You're not inverting it. You see? That's the difference, yeah.
So what is this? I don't know both.
Dynamic inversion. It's called dynamic inversion. So what they do in aerospace, like you have a nonlinear system, let's say some F function. They design a F inverse. Okay. So when you look from the input to the output,
The first problem is that F is a vector.
yeah,
So what is the meaning of the inversion?
you do that.
Each component will take the inverse.
Yeah, you take that.
Component
Yeah. And it will become identity. That's the main idea behind it. Yeah. It's the same. Yeah, they use it very well in the aerospace field. It's a problem. I never use it. The control guys in AA never use that. Only in aerospace you see a lot of people using it. Kalis, his name is Kalis. He's a well-known guy in aerospace. CALISE. He uses inversion. And very common in aerospace. So they put that in front of that system so that the overall becomes identity. Yeah. And naturally it will be always something's changing, and it is and people, they have analyzed it. It's been an old technique. But I don't like that, because if there is a singularity problem, you're stuck and it causes problems. Yeah. So like we do feedback linearization, right? They don't do that. They put the inversion. Kalis, if you look at the dynamic inversion, you look at any papers by Kalis, Anthony Kalis, CALISE. But a lot of people, Bernstein, there's a guy by name Bernstein, he's out he writes tons and tons of papers, That guy is in Michigan. Yeah, he's an aerospace guy. He also, and I can't understand any of his papers. But a lot of math, but he uses dynamic inversion. Yeah, Bernstein.
He used to write how to do research.
Is that right? Oh, is that right? No, but that's okay. I don't mind that.
No, the control system magazine.
Okay, yeah, he is. No, he's a good guy. He actually, but he puts a lot of math and very little practical value there. So, yeah, but all these guys publish in SAT.
Yes.
He works with another guy in Georgia Tech. Not I also know him, but he is a good guy, but we have a lot of discussions on this. Because are you engineer or are you mathematician? Anyway, but yeah. Any other questions, guys? Any other questions? We are a little early now. 10 minutes.
Ask whatever is coming in your mind. You can ask. That is the best opportunity.
Yeah. After next Thursday, you won't see me.
Whatever is, it may be a silly question. What is the problem? Ask something.
After that, virtual, nothing real. I don't know whether I'll come back here. Yeah, so. Any questions? I think maybe they should spend some time in running the, so you probably would provide the code today, right? And the slides maybe. Slides they have?
Slides already is.
You already shared with them. So
This slide is already with you. No, this one not. 5 and 6. Last slide 5 and 6 I have.
yeah. So the slides and the code, I think you guys will then play. And remember I told you in the afternoon, so maybe we should discuss a little bit. One is I want you to spend some time running the code, try to finish catch up. If you only have the example 1, I would rather have you do 2 things, right, in all these cases. One is without the actual NCS part, and the second was with NCS. And we did that for linear. Then we went into nonlinear and we did the same thing, right? Remember, we had the without NCS, with NCS. So I would rather encourage you to spend more time and read the slides so that you know where are, right? Tomorrow we have another tutorial. And again, I also want you to study the Lyapunov stability. Some parts I skipped because that was not applied to NCS. So I encourage you to study those also, so that you can see the difference between how it's getting into the actual expected value or into the stochastic domain. So remember we said asymptotically stable in the mean square. So you need to know a little bit and look at the book. You guys have the PDF. Look at the book about why is it called mean square. Because in the proofs, you get the norm and then you have a square on it. So I encourage you to go through all that stuff. Okay? So this will give you some background, and so try to finish at least the MATLAB code part of it. So how many, you asked them 2 problems, right? Inverted pendulum and the batch reactor.
But the other problems are also included there.
Yeah, okay.
If they want to try, they can try.
Yeah, they can try, yeah. It's very easy because it's just changing the system dynamics. Maybe you have to change the dimension of the vector. Yeah, okay? But it's all linear and positive, right?
One non-linear.
One nonlinear is there,
Yeah.
but you haven't shared the code of the nonlinear. Is there?
I've shared.
Oh, you did?
Problem 3 that.
Oh, okay, okay. I see. I didn't see that. That's why I was asking. Okay, so you have enough to do as part of it, and try to do that. That's the best way. You learn and you come back with questions. Remember? So tomorrow we have 2 classes. In the morning, 1 lecture, and we are slightly ahead, just 1 lecture ahead, you know. And then we have the afternoon, which is tutorial. Okay? All right. So we take a break.
Yeah.
All right. If you guys don't have any, yeah. Can you raise your voice because then others can hear you? Right. Ah. Oh yeah. Sure. And the same thing like we discussed, even if it's tracking, the only thing is you have to have the system control. Okay, that's number 1. The other difference is you have to construct another augmented system. I mentioned this to you. If you are using neural network. Because remember I mentioned if you are using neural network, the trajectory, which is in a tracking problem, is a function of time. Right? It's an explicit function of time. In a regulation, all this stuff we are doing is a regulation. In a regulation, the trajectory is a constant, either 0 to something or something to 0, right? So it's always a constant, right? So since neural network doesn't approximate over the compact set, I mentioned that, right? So you define a trajectory generator. Basically what you're doing is you're constructing the trajectory by like another state equation. Then you construct the augmented system with that trajectory generated state and the system state. That's it. And as long as it's controllable, you can do the same design. So you use the error now. Error is basically the desired state minus the trajectory. And there are papers available. You can look at it. Yeah. Okay? So it's no different. So her question was important. I was expecting that somebody asked you. So there are 2 basic control problems. One is called regulation. Other is tracking. If you do tracking, the same controller would work for regulation. But if you only do controller for regulation, it doesn't work for tracking. Why? You know that? You guys might have done that because you have taken the nonlinear control, you have taken some courses. So why is that? If you design a controller for regulation, it doesn't work for tracking. But if you do a controller for tracking, you can use it for regulation. No, even for regulation, you can, I just said. Okay. Put it as a question. Why a controller for tracking would work for regulation, but not vice versa? Okay, can you check and come back? So you could do that. You could do the same thing, but this question is if you do it for tracking, tracking is much more powerful because tracking you have the time. You have the time. So it's a lot more difficult problem than a regulation problem. Okay? Any other questions? But you can. The controllability has nothing to do with the tracking or regulation. It's basically with the system property.
So even for the, you're talking about the nonlinear, but even for the simple state feedback controller,
Yeah.
when you are doing the regulation,
Yeah.
the same control will not work for the tracking
Right.
because there will be a steady state error. You have to modify
That's right.
u equal to minus k.
Right. Right. I think that's what I want them to tell me why it doesn't work. It doesn't matter whether linear or non-linear. You're right. You're right. Because she was asking this question for tracking, why does it work, and the controllability side, it does no matter, but not in the design. Yeah. And that's why I want that to come back. What is that extra term? All right. Any other questions, guys? Any other questions? And he already has the answer. He already told, but I just want to see from you guys what exactly is that. Okay? Any other questions?